Okay, welcome to example number 7 in our discussion of reaction energy. The reaction energy is the difference of the energy that is caused by the difference of mass that either goes missing or is added in a reaction. That's called the reaction energy. So when a particle is incident upon a nuclei, there are several things that could happen. The particle could be scattered either elastically or inelastically. There could be particles that are emitted. All sorts of things. The amount of energy that is either released or absorbed depends on what happens. And that energy we're going to call the Q value. So we have, in any kind of reaction, we might have particle A plus particle B that reacts and gives you particle C and particle D. So to find the Q value, or that reaction energy, we take the mass that you start off with, mass A and mass B, and we subtract mass C and mass D from that. If the mass disappears, then there must be some energy that is released, and so we have an exothermic reaction. If the energy increases, then there must be some energy that was added to the reaction, and so then this is called an endothermic reaction. So what we want to do is look at these two masses. This change in mass is what we call the mass defect here. And so we're just using the Einstein's mass energy equivalence formula, E equals delta mc squared, to solve this kind of problem. So let's go on to example number 7 now. And so we have this lithium atom that is being bombarded by a proton, that's hydrogen atom here, and it releases a alpha particle here and another alpha particle, so two alpha particles. And so we're asked to find the energy that is released. So the Q value is equal to E, which is equal to delta M times C squared. Now, first thing we would do is we would look up all the individual masses of each of the atoms that are involved in this nuclear reaction, which has been listed already over here on the right side. Then we're going to calculate the initial mass. So the initial mass would be the mass of the hydrogen atom here, so 1.007825 U, plus we have the mass of the lithium atom, which is 7.016005 U, and we can calculate that. That gets you a mass of 8.02383 U, and then we're going to find the final mass, and that would be 2 helium nuclei. So we have 2 times 4.002603 U, and we get 8.005206 U. And you can see that the mass has decreased. So now let's find that change in mass. So we're going to subtract the larger mass, which is our final mass, minus the initial mass. So that is 8.005206 U minus 8.02383 U. And we get a mass defect of negative 0.018623 U. Actually, it's supposed to be 0.018624 U. And now we're going to calculate that energy, which is negative delta M times C squared. So we're going to put in your negative 0.01864 U multiplied by C squared. Now let's change this atomic mass units by multiplying by 931.5 mega electron volts per C squared for every atomic mass unit. So now we've converted our mass to mega electron volts, and then the C squares will cancel out here, and so we'll get an answer that is in just mega electron volt, and you get an answer of positive 17.35 mega electron volts. And this is a positive Q, which tells us that our reaction is exothermic. So it is giving off energy. And that's it for example number 7. And just to make one little note that I may have said incorrectly earlier, you'll notice that the initial mass here is greater than the final mass. So that means the initial energy of the system is greater than the final energy of the system. So that means that the energy must be lost because we have less final energy in terms of this mass. So there must be some energy that is being emitted and making it an exothermic reaction. Okay, and that's it for this one.